Okay, in the preceding then we integrated f of x, y, z equal xi plus yj. Picture looks like this around the unit circle. Let's just contrast that with what happens if we integrate this function, f of x, y, z equals negative yi plus xz, which, as we've seen, has a field, vector field, which on the unit circle looks something like this. Now, our integral is then going to be a closed integral around the unit circle. Now, a closed integral is often represented by an integral sign with a little bit of circle, a small circle, and unit circle just indicates that this closed path is the unit circle. Okay, and we're going to use the same parameters as before, same parameterization of the function. Y equals the sine of 2 pi I, x equals the cosine of 2 pi I, so that our sample point gives us the function as we see it here, with the negative in front of the sign instead of the positive that we had before. As we called it before, our f of x, y, z was this. Now we contrast with this. Our y becomes negative, this becomes negative. And our picture, again, becomes what we see. So, integrating this, if we follow all the same steps that we did here, the only difference is going to be that this sign here is negative, which makes this negative, so that when we do this dot product, we get a positive sine squared. Well, having done that, a positive sine squared plus a cosine squared is just 1. So we see that when we integrate f dot delta s, and delta s is identical to what it was before, delta s is just our parameterization, is just our displacement along one interval of our partition of our parameterization, of our parameterized curve. So that, again, delta s is identical to before. We're integrating around the same curve, we're just integrating a slightly different function. So again, this is our f, this is our dot delta s, and this is our result. And clearly enough, then we get the integral from 0 to 1 of 2 pi times the sine squared of 2 pi t plus cosine squared of 2 pi t. Well, same argument, sine squared, cosine squared, we get 1. So this is just 2 pi dt. And the integral is very clearly then just 2 pi. The integral from 0 to t of dt is just 1. The 2 pi factors out. We get 2 pi. And we make a side note, which certainly would not have been legible in the low resolution, that the magnitude of our function is just a magnitude, the square root of x squared plus y squared, and for this function on the unit circle, the magnitude of f is 1 at every point of the circle. So that when we multiply around the circle, when we integrate around the circle, and get the result 2 pi, 2 pi is exactly what we would get if we just integrated 1 around the circle, which is in fact what we did. And this shows that since the magnitude of f is always 1, and the integral of our component of f perpendicular, parallel to our path at every point is equal to 2 pi, then the function must always be tangent. We're always integrating the full value of the function when we integrate the tangential component, the component of the f tangent to the curve. This shows that the f vector is indeed always tangent, and of course it's easy to prove that by a number of other means.